Hello everybody, I'm Ladislav Kavan and this is a quick overview of my research. One of my favorite topics is physics-based simulation of elastic objects. Probably the most important example is the human body. Except for the bones, most organs are highly deformable, which is necessary for basic functions such as locomotion, breathing, or food intake. It's not just about humans, most animals have similar structure. So the classical tools to simulate elasticity involve continuum mechanics and finite element methods. And when I mention these keywords, most people will start thinking that we'll need a supercomputer, and even then we will have to wait a while to get the results. I'm coming from a different angle. I used to work on computer games such as Toy Story 3 or Disney Epic Mickey. And as you can see, games also need to simulate deformable digital characters. But the difference is in interactive graphics, the key is to minimize latency. The system needs to respond immediately to users' input. That means that we have something like 10 to 30 milliseconds to do all computations necessary to render the next frame. And to make things even more interesting, we typically have only a consumer-grade hardware, because not everyone can afford a supercomputer. By the way, it would be wrong to think that interactive graphics and games are just about entertainment. Interactivity is tightly coupled with creativity and problem solving, which can help us solve hard scientific problems, as exemplified with protein folding. Other very important application of interactive graphics are surgical simulators. Every new surgeon needs to be trained, and somebody will have to be their first real patient. So that sounds a little bit scary, but the good news is that simulation can help. Surgical simulators are basically boutique serious games, and real-time simulation of elastic objects is one of the key problems. Another area that has a huge need for interactive graphics is virtual and augmented reality. It seems that technology is finally ready to deliver high-quality yet affordable VR experiences. In VR, the latency of the simulator needs to be even lower, especially if you are also considering haptic feedback. So in all real-time applications where the user will be directly interacting with the simulated virtual world, low latency is the most important aspect, even more important than accuracy. Okay, so how can we speed up existing algorithms? Well, I think this is actually the wrong question to ask. I think the question we should be asking is what accuracy can we achieve in a limited amount of time, such as 30 milliseconds. So what does this mean for the simulation of elastic objects? To simulate deformable solids, we start from Newton's second law, which is discretized in time. In physics-based animation, it is common to use implicit Euler time integration, which is quite robust and much better than explicit methods, but unfortunately it's a little bit too slow for interactive graphics. So let me explain you the basics of implicit Euler time integration. So let's assume we are simulating Mr. Snail. So we discretize it using mass points, and we stack their coordinates into vector x0, which represents the initial state of our system. And we want to compute how the system will evolve in time. So we discretize the time axis using constant step size h. In interactive applications, this would ideally be equivalent to the frame rate, such as 30 milliseconds. Now let's assume we have already simulated our system for a certain number of steps. So that means that these states have already been computed, and y is some constant that depends on these previously computed states. I will elaborate on what y means in a minute. Now, the next state we want to compute is called x. I'm coloring it blue because it's the unknown. That's what we want to compute. And how do we compute it? By solving the following minimization problem. So that might look a little bit scary, so let me explain what this means. So first, the symbols. The x, as I mentioned, that's the unknown. That's the next state we are trying to compute. Y is that constant that depends on the previously computed states. So what y means, it represents purely inertial motion. Y is the state where the system would go if there were no forces acting on it, exactly according to Newton's first law. Now m is the mass matrix, h is the time step, and E is an elastic energy. So this optimization problem can be derived from Newton's second law using finite differences, but I can also explain it intuitively, and I prefer this intuitive explanation. The first term can be recognized as inertial potential, and the second term as elastic potential. So what implicit Euler is doing is seeking a balance or a compromise between inertia and elasticity. So speaking of elasticity, the simplest elastic model is Hooke's law. So we'll start by giving our snail some springs, And the elastic potential of each spring can be described by this simple formula. So if we have a spring and K is the stiffness of this spring, and P1 and P2 are the spring endpoints, and R is the rest length of the spring, then the energy is governed by this formula, which looks simple, but unfortunately the resulting elastic energy, once we add all these springs together, is nonlinear and non-convex, and that complicates things. Because the typical way to solve this optimization problem is using Newton's method. And as we know, Newton is an iterative method which computes the Hessian at each iterate to find a good descent direction. So if we look at our objective, we can see that the inertial term is convex, but the elastic potential is none. And this turns the entire problem to be non-convex. The non-convexity implies that the Hessian can be indefinite, which is a problem we have to address somehow, for example by regularization or some other semi-definiteness fixes. And to make things worse, we have to consider this over and over every iteration, because every iteration we get a new linear system to solve. So in summary, Newton's method is a little bit too slow, not quite ideal for interactive applications. So what I propose instead is to reformulate this optimization problem, specifically for interactive physics. So the idea is to decouple the problem into a large but convex quadratic problem, and lots of small but easy to solve non-convex problems. So here is the key idea, here's how we do it. The key idea is to rewrite Hooke's law using a projection. So let me try to explain that carefully. So the term inside the norm, P1 minus P2, is a 3D vector. And we can project it onto vector D, which has unit length. Now Hooke's law can be written as a square distance between P1 minus P2 minus R times D, where R is the rest length of the spring. And with some math you can show that this is exactly equivalent. This is not an approximation, this is just rewriting of Hooke's law. Now the main idea here is that the projected directions D can be introduced as new auxiliary variables into our optimization problem. And that's why I colored them green, because they are a special type of unknowns. So if we take the original implicit Euler problem and introduce these auxiliary projection variables Di, one for each spring, we will end up with the following optimization problem. After some matrix algebra, we'll distill it to this form, which has some constant matrices A and B and a constant vector C. And again, you can show that these problems are equivalent. You're just rewriting of each other. The one interesting thing about the reformulation below is that now the non-convexity is exposed as a constraint. Here the norm of di equals 1 is obviously very non-convex constraint, and here it's exposed. But the main point of this reformulation is that now we can use a different numerical solution procedure. We specifically use alternating optimization. The idea is that if we first fix D, we are left with a convex quadratic problem, which is quite beautiful because the matrix A, not only it's positive definite, but most importantly, it's also constant. It's not changing from one time step to another, which means that we can pre-compute its factorization and then the solves become very efficient. On the other hand, if we fix X, the solve for D becomes also very easy. Because if in the case of springs, the D's are just projections, so that means just normalization of a 3D vector. That's not very difficult. So the high-level picture of our solver looks like this. First, we solve many small non-convex problems. Then we feed the solution as a new right-hand side to a large sparse linear system, which has already been pre-factored, so we are only performing back substitutions at each iteration. This results in a new set of small non-convex problems, and we iterate this entire process. So how many iterations do we need? Well, it turns out that in practice this works surprisingly well. Already with one iteration, we obtain a nice stable animation, and you probably cannot tell the difference between 10, 20 iterations or the fully converged solution. So the next logical question is, how does this approach compare to traditional Newton's method? So in this graph we made an experiment. We took one example frame from a class simulation and compared the speed of our alternating solver here to Newton's method. And note that this is a log-log plot. We can see that our method actually needs many more iterations to get to the same level of accuracy as Newton. However, it's important to realize that each iteration of Newton's method is actually much more expensive because Newton needs to solve a new linear system at each iteration, while our method only performs forward and backward substitutions. So a more realistic comparison, we plot the error with respect to computational time for our method, and we compare it to Newton's method with a direct solver, and we also tried Newton's method with preconditioned conjugate gradients, but that only made it slower. So in this graph, we can see that our method reduces the error very quickly early on. Newton's quadratic convergence finally catches up and beats our alternating solver. But look where that happens. That happens somewhere in the range of 10 to minus 11, which is quite ridiculous accuracy for physics-based animation. And if we are doing interactive physics, we only have 30 milliseconds, which is here. So whenever time is limited, our method can give us a more accurate result. Okay, so far I explained how to make implicit Euler time integration fast. And in the second half of the talk, I would like to discuss some specific applications related to simulation of the human body. So in general, in the past decades, computer graphics transformed film, games, and visual effects. Movies like Pixar Monsters or Avatar: Lord of the Ring would have been impossible to produce without computers. So my question is if we could make the same impact in medicine. And I'm of course not the first person to think about this. Surgical simulators and robotic surgery are becoming increasingly important in modern medicine. And computational methods are also highly relevant in orthopedics and biomechanics. I started collaborating with surgeons several years ago on a project called Anatomy Transfer. I proposed the following problem. 3D anatomical models have been created for the average male and female subjects, similar to medical atlases, which students are usually used for training. But of course, nobody actually has the average body shape. So the question is, can we transfer a detailed anatomical model to a new target shape? The target shapes don't even have to be strictly human. We are curious how far we can push this. So the main idea of anatomy transfer is to solve Laplace's equation. First, we need the boundary conditions, and we obtain them by registration. So for example, here we register the source shape, a sphere with a target blob, or whatever that is. And then we use these Dirichlet boundary conditions to solve the Laplace's equation, which gives us a well-behaved deformation of the interior. And this is just the basic idea. We had to add some additional constraints to preserve the anatomical realism, like not to bend the bones and so on. But let me spare you the details and just show you some of our results. We managed to create anatomical models even for cartoon characters, quite different from the input template. And we also tested non-human creatures, such as this werewolf. We can of course animate the resulting anatomical models using standard techniques to create some interesting visualizations. Another project I would like to talk about is anatomically accurate motion capture. So this is quite a recent project, and even though we already have some results, this is still a work in progress. So motion capture is a fairly mature industry. It's used a lot in film, games, and visual effects. Unfortunately, the accuracy of motion capture is limited by so-called soft tissue artifacts. The problem is that we would like to capture the motion of the bones, but we measure only the markers which are attached to the skin or a special motion capture suit, as you can see here. So if we want accurate bone motion, we have several options. The first is real-time MRI. Unfortunately, MRI is very expensive and time-consuming, and the machines offer only very limited workspace. There is really not much space to move in an MRI machine. X-ray provides much more generous workspace and it's faster, but the radiation, of course, presents potential health concerns, so these experiments are usually done on animals. Some brave humans went as far as drilling markers into their own bones, but that's probably the last thing I would want to do. So what we decided to do is try a different approach, which is maybe not as accurate, but is definitely not invasive and doesn't require any medical imaging. So specifically, we took traditional depth sensors and we combined them with personalized anatomical models. which is similar to anatomy transfer. The difference from anatomy transfer is that here we transfer not only the geometry, but also biomechanically accurate kinematics and skinning. So here is what I mean by adaptable anatomical model. We can resize the bones and the kinematics and skinning still works. It's still functional. Next, we take a moving human subject and capture it with multiple depth cameras. It's just 2. This is me performing some simple arm motions. And after some processing, the depth sensors give us a sequence of point clouds corresponding to samples on the skin. And we use them to adapt the template anatomical model to the given subject. Here is the optimization routine in action. And after we have this personalized anatomical model, we can use it to track the captured point cloud sequence and solve for the underlying bone motion. So here are some results from our current prototype. We can correctly capture even effects such as pronation and supination, as you can see here. We also developed a lower limb model. You can see a walking step here. And here is a kick performed by a different subject, one with a shorter leg. And these are all just preliminary results. We still have a long way to go to make it more accurate. So in addition to physics-based simulation, I got recently interested in biology-based methods, specifically mathematical models of growth. For example, muscle hypertrophy. Maybe even more important is atrophy, which can result from the lack of mobility, for example, when you get injured. So we explored this in a project called Computational bodybuilding. We use a growth model, which is similar to elastoplasticity. We decompose the deformation gradients into 2 parts, a growth part, which captures permanent changes of the rest pose, and an elastic component, which accounts for the fact that the growing muscle is there not alone, but it's surrounded by other soft tissues. And the growth model itself is relatively simple. At each point, the muscle expands in directions perpendicular to the muscle fibers. I always strive for interactivity, and here we were able to achieve it by using the alternating solver I mentioned earlier, and a specially designed volumetric discretization. So the idea is to use an auxiliary mesh called muscle envelope, and we create this by shrinking the skin until it reaches the muscles. And this is what allows us to cleanly separate the muscles from the subcutaneous fat tissues, as you can see on this visualization. So here is an example result. We are simulating the hypertrophy of the biceps muscle. And note that as its volume expands, it pushes the surrounding tissues out of the way. Then we also proposed the model of fat growth by treating the fat essentially as a semi-fluid material, producing some interesting results. And we combine this with the method to change the length of the bones and the surrounding flesh to obtain bodies of different heights and proportions. So putting this all together, we created a system that allows us to create lean but also highly muscular subjects. We experimented with several different types of obesity, as you can see here. We tried to do very short and very tall or even taller subjects. And we also try to combine the growth of both muscles and fat tissues. And this is probably a good time to quit. If you want to see some more, please visit my website. And if you have any questions, please don't hesitate to send me an email on this link. Thank you.